Hi everyone, my name's John Freilich and I'm a professor in computer science at the University of Washington. And today I'm excited to talk about our research on scalable techniques to map and assess sidewalk accessibility. I want to start with a question. What problem do you see in this image? That's right, a lack of curb ramps. Despite decades of civil and disability rights legislation, our cities remain inaccessible. There are physical barriers, incomplete sidewalks, surface problems due to weathering or natural growth, or in the worst case, multiple problems in the same scene. And the problem is not just a lack of accessible sidewalks, but a lack of data. The U.S. National Council on Disability notes that they could not find comprehensive information on the degree to which sidewalks are accessible. Although physical, on-site walkability audits are the gold standard, they're laborious, expensive, and occur infrequently. So our research lab is pursuing a twofold complementary solution. First, to develop scalable hybrid human plus machine learning techniques capable of mapping and assessing sidewalks from across the world. And second, to leverage this data to enable new urban accessibility visualization and analytic tools. For example, in the background you're seeing a video of our tool Access Score. Here, users can get an at-a-glance custom view of the accessibility of their city based on the data that we're collecting. Our most recent crowdsourcing effort is called Project Sidewalk. With Sidewalk, online crowdworkers label and assess sidewalk accessibility by virtually walking through city streets using immersive omnidirectional street imagery, similar to a first-person video game. Labeling is a three-step process. You find the label type, rate the severity of the problem, and enter an optional description. Here we're labeling curb ramps and missing curb ramps. Or a fire hydrant is an obstacle in path along with an electrical pole. Finally, you can label missing sidewalks. In an initial pilot deployment, thousands of Project Sidewalk users virtually audited the entirety of Washington, D.C., labeling over 260,000 sidewalk accessibility problems with 92% accuracy. Working with local partners and NGOs, we have now deployed Project Sidewalk into 7 cities. Thousands of users from across the world, including Germany and India and China, have contributed nearly 425,000 labels and 100,000 label validations. Here's a top-down image of Sidewalk, showing 100,000 plus labels. The purple dots are missing sidewalks, the red are missing curb ramps, the orange surface problems, and the blue dots are obstacles. We've also been collaborating directly with cities. For example, here's the Public Works page from the city of Newberg, Oregon. Here, over 500 people have participated in auditing the entirety of city. Using our data, the Newberg City Council recently authorized $50,000 for immediate sidewalk repairs on city property and established 2 grant programs to help homeowners fix sidewalks outside their homes. Finally, as a last example, we recently partnered with Liga Peatonal, a Mexico-based NGO focused on pedestrian improvements to increase the safety and accessibility of public spaces in Mexico. We've now deployed Sidewalk in 2 Mexican cities, San Pedro Garza Garcia and Mexico City. In San Pedro, we're working directly with the local government. In less than a month, we've collected over 11,000 accessibility labels, and 1,000 plus users have contributed. There's now a growing community of users online that are sharing about our tool. The unprecedented number of image-based sidewalk accessibility labels allows for interesting new research and future work. For example, using the manual labels from Project Sidewalk data, we recently trained a convolutional neural network to automatically find sidewalk problems like missing curb ramps and obstacles in path. We've also been adapting our techniques to explore semi-automatic tracking of accessibility features over time. So, for example, here a user labels a missing curb ramp in an image from July 2015, and that label is back-propagated throughout time on that street intersection. Finally, we've been exploring new techniques to model and visualize urban accessibility as a function of sidewalk accessibility. And all of our data and tools are open source, a key ethos of Project Sidewalk, so others can build on our work. For example, Barbara Moreno, someone we've never met, built this interactive tool visualizing sidewalk accessibility in Washington, D.C. from Project Sidewalk data. This work received local press. Others have imported our data into online tools like Carto.com. In conclusion, I invite you to join our efforts in using hybrid crowdsourcing plus machine learning techniques to scalably map and assess urban accessibility. I want to acknowledge an amazing set of collaborators who have been fundamental to this work, spanning high school, undergrad, and graduate students. Initial research that led to Project Sidewalk began in 2012 as part of my first PhD student, Kotaro Hara's dissertation project. I also want to acknowledge Mikey Sogstead, who joined us as a master's student and is now a full-time research scientist and lead engineer on the team, and Manaswi Saha, who is currently doing her PhD dissertation exploring urban accessibility visualization and analysis tools to inform policy. I also want to thank our funding sources, including NSF, Google, IBM, Sloan Foundation, and the Pacific Northwest Transportation Consortium. Join us in mapping the accessibility of sidewalks across the world, and reach out to us if you'd like to collaborate. Thank you.